So, welcome to this next class, plant-wide control system design procedure. Like I said, we want to refine whatever we are doing into a systematic procedure. Control system design procedure. This was proposed originally by Lieben et al. I think it can be further refined. Those refinements I'll talk about later on. Step 1, define control objectives. Step 2, count control degrees of freedom, and once you have counted the control degrees of freedom, steady state operating degrees of freedom, etc., everything comes out from there. Number of independent valves, okay. It all comes from valves. Okay. Number 3, you see, particularly in chemical systems where you've got reactors and most of the reactions are exothermic, instability in exothermic reaction systems can be quite a big problem. Okay. So, you want to make sure that your reactor is stabilized properly. Okay. So, this is what they call establish energy management system. This is particularly relevant to energy management, basically done to effectively stabilize the usually exothermic reactor. Why is it necessary? Because temperature runaway is something that is simply not acceptable, okay, because it can lead to disastrous consequences. Okay, so define control objectives is straightforward. Okay, so we want, what would be your control objectives? What quality grade, any safety considerations, any environmental discharge regulations, you cannot discharge more than this, more than this amount of CO2 or whatever it is, H2S. Okay. All this come under control objectives. What do you want to produce, what quality, and what can you discharge, and so on and so forth. Any safety considerations, one of the very crucial safety considerations is particularly systems in which there is oxygen. If you have got oxygen, then what happens is you have got hydrocarbon, you have got oxygen, spark will come from somewhere and the fire triangle is complete, you can have an explosion. Now, what happens is any mixture will not burn for any composition range, right. Let us say you got a hydrocarbon fuel oxygen mixture. If there is too little fuel, then obviously the fire will not go. Also, if there is too much fuel, then you will be oxygen starved. So, you could be in the fuel starved regime or you could be in the oxygen starved regime, fuel starved. So, typically any hydrocarbon will have a lower flammability limit and an upper flammability limit, and you must make sure that if, for example, ethylene oxide, so you are putting in ethylene and you are putting in oxygen and you are producing ethylene oxide, right. This system will have flammability limits, and you have to make sure that nowhere inside the plant, until oxygen is removed, the composition is in the flammability limit. So, that is a very standard safety consideration. Okay. That if you are feeding in oxygen, the whatever mixture you have, it's never in the flammable composition region, significantly far away from the flammability region. Does that make sense or no? Yeah. So, control objectives: production, how much to produce, product quality, safety considerations, environmental regulations, etc., etc. Degrees of freedom, you know how to count them. Now, the next question is, what do you do with those degrees of freedom? You see, because stabilization is a fundamental objective, and usually the place where things can go unstable is the exothermic reactor. Therefore, you put in the energy management system in the beginning itself, when you have maximum freedom in terms of what you want to pair with what, right. Once you have paired it, that valve is gone. Anything else, you will have to use some other valve, right. So, therefore, it is a question of prioritization. What do I want to prioritize the most? And Liebman and company say that, well, to ensure that there is never a possibility of a runaway no matter what, you first put in a control system that ensures exothermic reaction heat is effectively removed to utilities. Yeah. Therefore, it comes up high up the order. Okay. Step number 4, set production rate. This is the same as saying set production rate is the same as saying what? Choose the TPM, choose the throughput manipulator. Many a times, because your local plant is operating in an integrated, for example, a refinery complex, okay, many a times either you will have to process what the upstream process is feeding, in which case the throughput manipulator is at the process feed, or you will have to supply a downstream process whatever it is demanding, in which case your throughput manipulator is at the product stream. Okay. Sometimes you also have large surge tanks. So, you can operate this plant without having to worry what the upstream or downstream plant is wanting or asking you to process. In that case, you can choose the throughput manipulator wherever you want. Okay. So, set production rate, choice of throughput manipulator, that is a subject in itself. We have dealt with it a little bit. You know, if you are free to choose where to put the throughput manipulator, put it at the bottleneck constraint, right. But if it is being dictated to you that no, you have to supposed to process this much, or if it is being dictated to you, well, you have to supply this much, then it is not a choice. That depends on the exact way, the operating philosophy of your integrated refinery complex or petrochemical complex or whatever you have. Okay. But the point is, where do you set the production is a design decision. Okay. Now, number 5 is control quality. Safety and other would include environmental, etc., and other important objectives, production objectives. Okay. Now, you see the way it is being, the way things are being prioritized. First thing, I want stable operation. Therefore, I say, well, energy management should be done when I have maximum number of valves available to me. Then I can get the best pairing for that. No matter what, it's going to run proper, nice and proper. Okay. Then production rate, and if production rate is a degree of freedom or is a design decision, I will choose it at the bottleneck constraint. Okay. But then when you are producing whatever it is you are producing, quality will always be something that you want tight control of, right, because you do not want to sell anything. If you are saying 99% pure and you are producing 99.5%, you are not charging any money for that 0.5%, right. and that 0.5% raw material is getting consumed, right? So that's actually a big loss. Yeah. So after setting the throughput manipulator, you want to put in place a control system that will give you what? Tight product purity control or product quality control, right? The tighter the control, the less the quality giveaway. The lesser the quality giveaway, the better off you are in terms of economics. Your raw material consumption will be that much less. You can always produce 99.9% pure product and guarantee that it is 99% pure, right? That 0.9% is extra loss for you because you are consuming raw material for that, not charging anything for it. Yeah. So you set your throughput manipulator, or in the operating philosophy of the plant it is either being set at the feed or at the product. Okay. Then you still have lots of valves left. Like you have only taken valves away for what? Tight reactor temperature control or removal of reactor heat, production rate. You still have lots of valves left. Those lots of valves that are still with you can be used to do what? Achieve tight product purity control, because that helps you economically. Also safety. Why is safety important? Because if an unsafe condition is highlighted and logged, you are duty bound by regulation to, for example, take a shutdown and then restart or whatever, right? And a shutdown is essentially loss in production. That is simply no. So you also want, if there are safety concerns such as ensuring that flammability limits are respected, you are always away from the flammable region. Well, that has to be done real tight, because should it go in that region, there is no other option but to shut down the process, right? That's a big loss. Okay. Similarly, environmental regulations, because if an inspector comes, either you have to bribe the chap, right, which is again a loss, or that guy penalizes you, which is again a loss. Yeah, you don't want that. All right. So you need to put in. So when you have all these degrees of maximum number of valves available, what do you do with them? Well, you prioritize so that, okay, I always want good quality product, on aim, on target product quality. So let me put in place, when I have maximum available valves, tight quality control, safe operation, zero discharge. Okay. Once I have done that, then control inventories. When I say inventories, I mean surge capacities, maybe pressures, even component inventories. You have to make sure that component inventories do not build up, and we've seen examples of that, right? Control inventory. So put in place your inventory control system, your level controllers, your pressure controllers, right? And it is in this context that the radiation rule becomes important, that we have seen. And this control inventories is essentially ensuring that material balance is respected, local as well as global, not only for your local unit but also overall for the plant, right? Number 7, this is called Downs drill. What do you mean by Downs drill? We are essentially saying that make sure that double check that everything that is coming into the process has a way out, right? You have put in place a control system. Now you want to make sure that everything that is coming in has a double check, that everything that is coming in is either consumed or it has a way out. This is double checking basically global material balance. Okay. So Downs drill is check. component inventory balance. All the species that are there in your system, make sure that they are either consumed or they have a way out.
It's a part of control inventory.
It is, but you want to double check. You know, it's subtle. Because it is subtle, you do something and then you double check. Okay, so this is essentially a double check. Okay, so check component inventory balances. Number 8, usually after doing all this, you will still have some valves that are left. What do you do with them? You essentially put in loops for better control of each of the individual unit operations, whether it is a distillation column or a reactor or an extractor or an absorber or whatever. Okay. So, what should I say? What's good English for that? Refine control system for individual unit ops. Okay. Last but not least, optimize. If you still have valves that are left, well, use them for optimizing or refining. I would say refine, further refine dynamic controllability or economics. And to improve economics, you can also adjust some of the set points. For example, recycle rate can be increased so that side reaction is suppressed. Okay. So, now you are using the recycle rate degree of freedom to improve yield, right. These issues are left for the end in this procedure, but philosophically it is a sound procedure in the sense that you are ensuring that your reactor can never go unstable by using the best degree of freedom first. Then you are doing tight control of everything else that is important: product quality, safety, discharge, environmental discharge, right. Only after doing that are you controlling inventories, because tight control of inventories is not really important. As long as the level inside a tank is, let us say, between 30 to 70%, you are okay. Yeah, it is only when the level goes beyond 80% or below 20% that some alarm comes, and then you need to make sure that that level gets controlled, otherwise the tank will run dry or it will overflow, some unsafe condition will develop, right. So, tight control of inventories is not really important as long as the inventory is not building up indefinitely or not depleting indefinitely, right, you are okay. Therefore, this inventory control is step number 6, low down in the hierarchy of steps, right. So, what is most important? Do it first, next, 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 next. And therefore, inventory is controlled in the end. Yes or no? To that end, I would also like to point out, for example, if you got a distillation column, number of valves is 5. Degrees, steady state degrees of freedom is only 2. No matter what you do, 3 valves are always going to be available for inventory control. Level here, and pressure. Yes or no? So, I really do not know if, well, the philosophy is clear. What is most important? Do that first. And that is the mindset from which this procedure has come. What is most important? Do that first. Most important, reactor should not run away. Well, put in place. By the way, establishing energy management system. Well, it is always, you see, this is intimately linked with the way the reactor is designed. So, for example, if the reactor is mildly exothermic, if it is mildly exothermic, you know, you have a CSTR, let us say, a jacket would be enough to remove the heat. So, for example, fermentation reactors, biochemical reactors are of that type, because the reaction is mildly exothermic. Jacket is enough to remove the heat. If exothermicity of the reaction is more, what will happen? You see, volume blows up faster than surface area. Even though you can remove the heat in a test tube, the moment you want to run it at an industrial scale, well, your reactor becomes really big, but surface area doesn't blow up as much, and now the jacket is not what test tube you could cool in a bath. That's not enough for an industrial reactor. And then what you have to do is, well, the heat has to be removed, otherwise the reactor would be unstable. So, what do you do? So, you start exploring add-ons. What are those add-ons? Add-ons or alternative designs. So, you could have an alternative design such as a cooling coil. Cooling coil will give you a lot of, well, if it is still much more exothermic, exothermicity is more, and you know, the amount of, the coil, the heat transfer area that you can get by putting in a coil is not enough to remove the reaction heat. What do you do then? Any idea? What do you do then? Well, you can do what you can do is take the reactor material, send it through an external heat exchanger. Right? You just take the material from the reactor, send it through an external heat exchanger. External heat exchanger does not have any catalyst, so there is no reaction. Right? It's hot, but then the shell and tube heat exchanger has as much area as you want for heat removal. Yeah, and then that cooled material is sent back into the reactor.
FEHE.
This, it's not an FEHE, no.
That's for
FEHE is for energy recovery, is for energy efficiency. It's got nothing, you know. We'll talk
about.
about.
Also, like, used as a heat removal system. Say when we have.
It's not a heat removal system. It actually recycles heat. It recycles heat. So maybe we'll discuss it. Hold on, remind me. The point is, your reactor system will be designed in a certain way to remove the reaction heat. Right? So how would you, for example, remove heat if it's a jacket? Answer would be obvious. How would you remove heat if it's, for example, an external heat exchanger? Answer would again be obvious. How would you remove heat if it's a cooling coil? Answer would again be obvious. Does that make sense or no? Maybe I think I need to explain this a little more. So, for example, if you've got a CSTR, man, forgive my drawing, it's always pathetic, and I don't have any hopes of it improving. What's usually done in a cooling coil is, you have some amount of storage of whatever is circulating, let us say cooling water, that's circulating inside the cooling coil, inside the jacket, and then what you do is, you have a pump that's taking that water and circulating it through the. You also have cold water, for example, cold cooling water that's going in. Okay, and let's say material is coming out of the jacket here, it's going out here, and you have a. Is this clear? What's happening? Note that the recirculation rate is high. The pump is ensuring that the recirculation rate is very high. If the recirculation rate is high, what does that mean? That means the reactor essentially sees a jacket at constant temperature. Temperature rise is negligible because the recirculation rate is very high. So as far as the reactor is concerned, it is seeing a jacket which is at some temperature. Okay. How can you adjust that jacket temperature? How can you adjust that jacket temperature? By putting more or less cold water. If you put less cold water, jacket temperature will go up. Why will it go up? Because why will it go up? These things have to be thought through.
Residence time will increase.
Residence time is fixed, recirculation rate is the same. You are not changing the recirculation rate. If I reduce the amount of cooling water going in, what will happen to the jacket temperature? Why? Jacket temperature will increase. Question is why?
So there is less water to absorb the heat.
So no. Yeah, there is less water to absorb the heat, that is true. If you look at it as an overall system,
Amount of water as a mass is less.
well, what is recirculating inside the jacket is the same. It's just that it's hotter, right? If it is hotter, what does it mean?
Delta T would be less.
It's because of the delta T. Delta T is more. Okay, I think the inverse problem is easier. If the reactor temperature is increasing, what would you do?
Circulate more.
You'll increase the cooling water, right? If you increase the cooling water, what happens? Jacket temperature goes down. Jacket temperature goes down, delta T goes up. Heat removed across the reactor wall goes up. The increasing temperature comes back. Yes or no? So this is what is actually done. What you do is, okay, of course, now the control system is pretty obvious, right? You have a jacket temperature controller, and this jacket temperature controller set point is coming from a master reactor temperature controller. Yes or no? Okay. So the point is, if this is the heat transfer arrangement, well, this is the control system that's going to get put. Yes or no? All right. Somebody may argue, well, what I can do is, and this is where I think it's important to think these things through. What I can do is, for example, let's say the feed is cold. Okay, feed is cold. Some fellow says, well, look, my bottleneck is, my production capacity is limited by the amount of heat that I can remove in my reactor. So to maximize production, what I need to do is make sure that the cooling water flow is maximum, so that heat removal is maximum, and then I will control temperature like this, right. So basically what I am saying is, I have removed the rest of the circuit, okay, but basically what I am saying is cooling water is max. So basically what I have is, this is a fully open valve, fully open. The valve is fully open, so you are putting in as much cooling water as possible, and then you are sucking in as much cold material as can be sucked in, right. What is the problem with this control system? Is there a problem with this control system?
So if we change the input, then output will also change. So our TPM manipulator will won't work.
Throughput is essentially governed by this cooling water. If I reduce the cooling water, see, from a steady state point of view, if I reduce the cooling water, temperature will rise. If temperature rises, what do I, oh well, temperature will,
Low.
if I reduce the cooling water, temperature,
Rise.
so temperature is rising, so what will I do to the feed? I will reduce the feed, yeah, basically so that the amount of heat released is less. Yes or no? That is what I will do. From a steady state point of view, it makes perfect sense, but you will never implement this in practice. Why? You will never implement this in practice. Well, actually you may implement it, but well, I would say don't implement it anyway. The reason is as follows. It's a CSTR, right? CSTR has got a large hold up. If it has got a large hold up, let us say reactor temperature was going down. If reactor temperature is going down, what does it mean? It means that I can add, I can add more feed. So I start adding more feed. As I am adding more feed, the composition of the reactant starts to go up. That reactant builds up in the composition of the reactant slowly but surely. It will not happen immediately, but the reactant composition will start to go up, right? 10 minutes, 15 minutes down the line, the reaction rate, because of increase in concentration of the reactant, reaction rate will start, more reaction will start to happen. If more reaction starts to happen, what will happen? Temperature which was going down will turn around, and now it will start to go up. As temperature starts to go up, what happens?
Rate of reaction.
You see, the rate of reaction increases exponentially. Then what happens? Temperature has gone up. While that feeds the reaction further, temperature has further gone up, and it's further gone up, and it's further gone up, and then what you have is a runaway.
So when the temperature starts going up, won't we have a control?
But that takes a long time. You see, for the feed to affect the concentration and then for the reaction rate to respond to that takes a long time. Let us say 10-15 minutes. In that 10-15 minutes, once the temperature turns back and starts to rise, it can run away. At least the potential is there for it to run away. Do you see what I am saying? You could always have, this will not happen in a plug flow reactor, for example, because in a plug flow reactor, hold up is not as much. Things are flowing, it is like flow through a pipe. This is flow through a tank. So there is large hold up. Because of this hold up, change in feed causes a very slow change in the reaction rate, and therefore temperature control cannot be very tight. And in the excursions where the temperature is rising, you have the potential for runaway, right? So this will never be done in practice.
Basically due to the sluggishness.
Exactly. So your reactor can go unstable. You are using a manipulation handle which is not tight. You see, if something is stable, you want a manipulation handle, you change it and it has an immediate effect. Then you can stabilize it. Here what is happening is you are changing the feed. It takes a long time for the reaction rate to respond to that change. In that time, damn thing can run away, right? This is also the classic example. So you are putting in, you are adding fuel in the reactor. When the fuel catches fire, that means the temperature is turning back. You can't put out the fire. You see, it's very easy to light a fire. It's extremely difficult to put it out. So once that fuel that's accumulated inside the reactor lights up, well, a runaway is bound to happen, right? Therefore, this will never be done in practice. Okay. So that's what is meant by step number 3, establish energy management system. Okay. You want to make sure that your reactor temperature control is extremely tight. Okay. Now we come back here. Let us say economic objective still says that, look, I want to operate this so that production is maximized, heat transfer is limiting. What would I do? Heat removal in the reactor is what is limiting production. That is my bottleneck constraint. A great man called Shinsky. What Shinsky says is, take this valve should be nearly fully open, right? So I know this valve position. Okay. I have got a flow controller on the, let us say, the feed. This valve position controller makes a slow adjustment to the feed set point, and this set point is, let us say, I don't know, maybe 95%, maybe 90%. So 10% trim is there. Should there be a disturbance in the temperature, I can still adjust the cooling water valve. I will never input 100%, because if then the cooling water valve is 100% open, should the temperature rise, I will not be able to bring it back, right? That again makes it unstable. Yeah, but in this case, I will be operating my process at, on average, 90% fully open cooling water valve. Yeah. How does it work? Well, if the valve is only 50% open, VPC compares, well, valve is 50% open, I want to be 90% open. So what do? I need to increase the heat generation inside the reactor. How do I increase the heat generation? By putting in more reactants. So increase the feed to the reactor. Yeah. Yes or no? And this VPC, valve position controller, can be a slow one, right? So now I have tight control of the reactor temperature, right, and the VPC is ensuring that I am processing near max capacity. I am running the process at near max heat removal capacity, which is near max production. Yes or no? Yeah. Okay, so this is one, this is the way it will be done. You won't do it the other way. Why would you not do it the other way, where I was controlling the temperature directly by adjusting the feed? Because my system my reactor becomes potentially unstable. There is the chance of a thermal runaway. Yes or no? Okay. You were talking about feed effluent heat exchanger. See, typically what is done is, let us say there is some gas vapor phase reaction, you are heating it in a furnace to the reaction temperature, and let us say you are putting it into a packed bed reactor. Okay. Let us say it is a cooled packed bed reactor, and well, okay, let me do it the other way. You got a shell and tube heat exchanger. The tubes are catalyst loaded. Okay. The tubes are let us say catalyst loaded. So the hot reactant flows through the tubes. Okay. Reaction occurs and whatever comes out comes out. Whatever comes out is also hot. All right. Then let us say, to remove the heat, what we are doing is we are recirculating pressurized water at a very high rate. Since the recirculation rate is very high, very small temperature rise occurs in the water temperature. So the tubes essentially see a shell that is at constant temperature, whatever the temperature may be. Okay. UA delta T, heat nevertheless gets removed from the tubes to the shell, because the shell is colder, tubes are hotter. Okay. This goes to this steam drum. Okay. And in the steam drum, you see, what does a pump do? A pump pressurizes a liquid. So even if the liquid is at nearly the boiling temperature, under pressure it will not boil. Yeah, under pressure it won't boil, but the moment it comes into the steam drum, maybe there is a small valve here. Okay, near the steam drum there is a pressure reducing valve. So then the water loses pressure. Because it loses pressure, at low pressure it flashes. Yeah, so you get steam going out. Because steam is getting lost, you need to make up. So there is some makeup boiler feed water. So BFW, boiler feed water steam. Okay.
Why do you want to create steam?
Why do you want to create steam? Because okay, this has got some engineering reasons. Steam is water is available in plenty. So if you want to cool, you would rather use water than anything else. Anything else will be more expensive. Okay. Now because steam and cooling water are the most prevalent utilities. Okay. Wherever possible, you would like to generate steam. Wherever possible, you would like to consume steam, because anything else is too expensive, is much more expensive. Okay. So heat is being generated in the reactor, it is recovered as steam. Okay. Now let us say the temperature inside the reactor is 400 degrees Celsius, then you can't use steam, you can't generate steam. Why can't you generate steam? Because critical temperature of water is 375 degrees Celsius. Beyond 375 degrees Celsius, you can do whatever you want to the pressure, it will never condense. You see what I am saying? So steam is used, from say 100, 110 to maybe 250 degrees Celsius. Steam can be used. Higher temperatures, you may have to use something like cooking oil. Cooking oil won't vaporize even at, I don't know, 400 degrees Celsius, right? So there are these proprietary oils which are used as heating media for higher temperatures. You want still high temperatures, maybe 600, 700 degrees Celsius, then there is no other option, furnace. You just blast the damn thing, right? So it depends what is your operating temperature. If your operating temperature is such that steam can be used or can be generated, damn well you will do it. If your operating temperature is such that steam cannot be used or cannot be generated, well, you will do something else then. Yes or no? Okay. Why do you want to use vaporization? Because vaporization uses latent heat. Latent heat implies your, for example, this line where steam is being generated, kilograms per hour will be small than if you are using, let us say, no phase change but a sensible heat effect. Then the amount of flow that you would have required to remove the same amount of heat would have been much more, and then the piping and the valves would have been that much more bigger, etc., 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 right. So it is all for economic reasons. Why do you do it this way? Well, because this is the most economical way of doing it. Okay. Further, to improve the economy, what you would do is, well, the reactor outlet is hot, reactants are cold, they need to be heated up, you are doing it in a furnace, but you would be a fool if all of the heating is coming through the furnace. What would you do? You take the hot stuff, pass it through a process to process heat exchanger, right. So the hot reactor effluent is heating the cold feed to the reactor. Now what happens? The duty of the furnace goes down. Earlier, if all the load was on the furnace, you would have required this big a furnace. Now 50% of the 50% of the preheating load or 60% of the preheating load is coming from, this is the feed effluent heat exchanger, right. What does that do? Furnace heat is expensive, right. I have reduced the furnace heat. I have also reduced the size of the furnace. Furnaces are extremely expensive. That's because they operate at 800, 900 degrees Celsius to thousands of degrees of Celsius, and then the material that you have to use is expensive. Specialized alloys that will not melt, that can withstand those temperatures, etc., etc., etc. Damn thing is very expensive. Okay. So the smaller the furnace, the more economical it is, the less capital you have to invest, right. Therefore this is what is done. This is a feed effluent heat exchanger. So how would you remove the reaction heat? Well, how would you know more steam is to be removed or less steam is to be removed? By the pressure inside the steam drum. If more steam is getting generated than you are removing, the pressure will build up, right. So steam rate gets set by a pressure controller. That makes sense? Okay. How would you figure out whether more boiler feed water is to be put in or less boiler feed water is to be put in?
Equal the amount
Well, okay, so
we can
so you will ratio it. Well, what if the rates are not exactly equal because sensors are off?
liquid level.
Level, absolutely. So you can have it in ratio, and that ratio set point is adjusted by the level controller. Okay, I am just simply drawing it like this because of lack of space. Essentially, how much water you are putting into the steam drum is governed by, right? How would you decide? Or now you put in place this system to remove more or less heat. Okay, how would you remove more or less heat? Pressure is what it is, level is what it is. How will I adjust the heat removal rate inside the reactor? So, for example, let us say I put in more feed. Number of passes is fixed. Once you have designed it and put in place, so if it is 2 passes, 2 passes, if it is 4 passes, 4 passes, that can't be changed on the fly.
Feed rate coming out from the reactor, we will decrease it.
No, but that's it. That's it. It's like flow through a pipe. Once you set it, okay, you have decided this is the feed rate to the reactor. Let us say I increase the feed rate to the reactor. If I have increased the feed rate to the reactor, more reactant is coming in, more heat will get released. If more heat is getting released, what will happen? Delta T. Well, see, you have to think these things through. For example, the temperature of the outlet will increase. Okay. So, if the temperature of the outlet is increasing, that is telling you the reactor is heating up. You need to do what? You need to cool it more. How will you adjust the cooling rate?
More water.
No. What sets? See, cooling rate inside the shell and tube heat exchanger is governed by UA delta T. Area is fixed, heat transfer coefficient, flow rate is high circulation rate, it is what it is. So, you can't adjust this. What about delta T? Delta T is some average temperature of the reactor minus temperature of the coolant. Temperature of the reactor is not in your hands. Can you adjust the temperature of the coolant that's circulating, you know, the shell side temperature, which is nearly constant? Can you adjust that? This is not in your hands. Can you adjust TC? How?
We can cool the water.
What sets the temperature of the coolant, of the water? If the pressure is 1 atmosphere, what will be the temperature? 100 degrees Celsius, because steam boils at 100 degrees Celsius at 1 bar. Okay. So, let us say the pressure on average is, I don't know, 15 bars. Okay. And I find that the reactor exit temperature is increasing, so I need more cooling. What will I do to the pressure set point?
Increase the pressure.
I will decrease it. If I decrease it, steam will boil at a lower temperature, temperature of the coolant will go down, temperature of the coolant goes down means UA delta T goes up, the temperature of the reactor which was rising, because UA delta T has gone up, will come back. So, what you are doing is essentially this temperature control, which is setting this. Yes or no? This has got nothing to do with how much feed water you are putting in. You can put more or less feed water. If the pressure remains fixed, nothing happens to the temperature in the shell side. Is this clear or no? Alright. So, the mechanism has to, you see, once this is the heat transfer system you have put in place, bloody hell, this is the control system that you have to put in place. There is no other way.